Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap today, but before we get started, we do need to go over a few housekeeping items. First of all, today's event is being recorded, so if you miss any or all of the event, you will be able to access the webinar on demand. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your question. And we'll take a few minutes near the end of today's presentation and go through those questions. And finally, before the end of today's webinar, we will also be doing a random drawing for 3 $50 Amazon gift cards. So stick around and hopefully your name will be one of the 3 called. Okay, with that, we will get started with today's webinar, which is monitoring containerized application environments with eBPF. Our speakers today are Daniela Ponce, who is Senior Product Marketing Manager at InfluxData, and Luca Derry, who is founder of ntop. Welcome to you both. Thanks for joining me today.
Hi, Charlene. Thank you for the introduction. Hello, everyone. This is Daniela Pontes. I'm Senior Product Manager at InfluxData, and I'm here today with Luca, founder of ntop, to talk about monitoring application environments, containerized application environments with the eBPF. But first things first, sorry, let me reduce this. First thing first, what is InfluxData? InfluxData is the open source time series database. You may have noticed a healthy amount of pride in that statement, and it's for a good reason. We believe that we provide means for improvement, and we do that by giving you real-time visibility into stacks, sensors, and systems. A little bit more about InfluxData. We were founded in 2013. We have our headquarters in San Francisco. We are about 115 employees, full-time employees, half of them being technical positions. Our mission is to be the modern engine for metrics and events, and we do that by providing a time series data platform where all your timestamp data can converge to. We focus on 3 main sources of timestamp data, which are sensors, infrastructure, and business process monitoring. We differentiate by being purpose-built. In every decision we made in the design and architecture of the solution, we kept in mind that we want to provide the fastest time to awesome. Our presence in the market today is about 200,000 unique active deployments and more than 500 customers. Some of them you may know: IBM, Cisco, PayPal, SAP, Comcast, Tesla, Siemens, to list some of them. We are actually in practically every segment, and along with market leaders. Our business model is an open source distribution with closed source economics. So InfluxData is the company behind, a vibrant and motivated open source community. We provide brain power into that community, and we offer value-added kind of deployments. If you are interested in high availability clustering and hardened security, we have the enterprise offering. And if you don't want to host your own equipment, we have a cloud offering. Just to give you some insight into the market, we keep close attention to the database market. Every month, DB engines provide reports. And on your left side, you can see that time series is actually the fastest growing segment in the database market. We grow faster even than other modern kind of database like graph and popular ones like search. On the right side, you can see that InfluxDB inside of the time series database market stands out completely. And that includes not only open source, but also proprietary solutions. We are clearly the preferred choice. Let's talk a little bit about market drivers, because what is the big news about timestamp data? We have been doing this for a long time, and that's why we know that if the economy is doing good or bad, and that we are hurting the environment. The news is about the amount of data that has been collected and is being collected in terms of time-stamped information. And that is a result of two main forces. One is the sensorification of the physical world. And that includes, the smart cities telling you where to park, or telling first responder teams, the fastest route to where they need to go. But also include this whole IoT umbrella of gas, oil, renewable energies company monitoring everything that they do. The consumable IoTs, giving back to you services about your own time series, like telling you how much you have exercised that day, that your vitals are doing good. So there is a huge market created around collecting timestamp data. On the right side, we have another strong trend, which is what is going on with the virtual world. It's a universe that is being reshaped. Applications are broken into parts to keep up with the pressure for faster rollouts and updates and new features coming to the market. And that means that what once was one is now, many. And before, you needed to monitor 5 to 10 metrics, including, your CPU load, memory, your disk space, network interface. Now you multiply that by the number of pieces that you broke your application into. And by the way, now that they are not together, you have a network that needs to make sure that they talk efficiently, and you need to monitor that as well. And not only that, you have these application modules, which are services or independent processes running inside of containers, and containers are put into pods, and pods are orchestrated in frameworks like Kubernetes. And now they come and go as you wish in terms of resource assignment. So that network is not only vital to make the pieces work together as a whole, but is meshed, and it is morphing constantly. So the pressure on network monitoring is huge. Let's talk a little bit about network monitoring. We see it as based on three main pillars. One is availability. So you want to make sure that you can go from A to B, and everything that's involved in the process is doing its job. It's up, it's healthy, and the route is performing. It's okay. You can do that route. And for that, we have solutions for you. It's open source. It's available. You can start using. You can start monitoring the availability of your network. We have Telegraph agent. You can send everything to InfluxDB, visualize, and set alerts on. All good with regards to availability. Then another pillar in network monitoring is responsiveness. Okay, you can go from A to B, but how and under what conditions? What is the latency, packet loss, error rate, jitter? And by the way, how your network interface is doing? Is getting clogged, jammed, and that could impact, the delay in your network. So you want to make sure that the network not only writes correctly, but provides the right conditions for the applications that you run on top. But good news for you, there is also solutions available, and InfluxData platform gives you already plugins like Telegraph Ping plugin, as SNMP plugins that can collect that data, brings everything into InfluxDB, and again, you can monitor with pre-canned dashboards ready for you to use, and you can set up your alerts, and everything can be under control. And the third pillar of network monitoring is traffic monitoring. That is actually a very important one. It's about knowing who is using this nice network that you put in place and that you keep a close eye to, making sure that everything works fine. So you need to understand the flows running in that network. We make sure that it is legit, it's not malicious, malformed, it's not a sign of any kind of attack. And for that, you need to understand packets. And good news for you is that we also have a solution for you. InfluxData with its partner ntop provides you visibility into flows. You can see what is generating flows from what is the IP, what is the protocol, what is the port that is consuming your bandwidth. And from that information, you can make your decisions. And so always good in the world of network monitoring, right? Not really. With containers, the game changed. You now have situations when you have some of your services running inside of a pod, and they talk to each other, and that conversation never really reached the network interface. There is never a packet for you to look into and make your assessments. So in this new world of containerized applications, you need to have another window to look inside of your traffic and understand what's going on. But the good news is that we have already worked on it. And this is a good time for me to pass the talk to Luca Detti, who is going to talk to you about eBPF and how this can help you with network monitoring.
Hi, Daniela. Thanks for the introduction. Yes, the idea is exactly what you said. So in essence, to provide visibility to the network and to, in essence, let people see what is happening, not just on a standard network, but also on a containerized application environment. This is where eBPF comes into the game. So I will now tell you a few words about ntop. So we are a company based in Italy that we develop mostly open source network traffic monitoring applications. We have started about 20 years ago, and since then we have spent a little bit of time in network monitoring, but also in other areas such as high-speed packet processing, deep packet inspection. So we have a toolkit named NDPI that is available on GitHub as most of our code. Also on cybersecurity, where we try to fill the gap between monitoring and security, so that we don't not just see what's bad, but we also stop threats as much as possible. So part of our activities is basically network traffic monitoring. So that is the core of our company. What is that about? So in essence, if we look at Wikipedia or to any other online website, it is defined as, in essence, a way to ensure availability and smooth operations on a computer network. And typically, this is performed through network sniffing. That means that we have to capture packets, try to understand what is happening by reconstructing the network flows of communication, and then based on that, generate some metrics such as retransmission, delay, latency, bandwidth, and based on that, see whether we are in good shape or not, if there are some users that are affected by certain type of problems. And because of that, we have to fight against the network speed, because every year or every at least 2-3 years there is a speed bump. So when I started to do this in 1998, 1 gigabit was already a very high speed, and now 1 gigabit is mostly commodity. Actually, 10 gigabit is commodity on the server. 1 gigabit is commodity at home. So this means that we have to process more and more packets, and that the amount of information that we receive is always increasing. Because of that, we need to find smart ways of doing network traffic monitoring without using the whole CPU cycles simply for processing packets. But traffic monitoring is interesting, not just because it's a fascinating topic, but because in essence we have to do measurement, and with a measurement it is possible to improve certain situation, because otherwise we simply have to rely on users, so that whenever they can come and complain that there is something wrong, we have to fix it. Because this is not a good approach, the idea is that we have to instrument our devices and our systems so that it is possible to provide data, so that whenever there is a problem or a user complains, then we have some evidence of the problem in case something bad happened, or we can report to the user, okay, this is due to a certain misconfiguration, or at least provide a positive answer to the question. So it is very important to monitor. And in order to monitor, in order to provide service, we have to make sure that we have control over our devices and our services. And it is not possible to do that unless we are able to see what is happening with high level detail, so that we can monitor not just volumetric data, such as number of bytes, number of packets, but also to care about metrics that are becoming more and more important, such as latency. And this has to be correlated with users, with processes, and today we are talking about containers. So it's important not to just provide a number, but to also put this number into a context and to see whether, based on a certain activity, this number is good or not, and in case it is not that great, do some improvement. This is the goal of traffic monitoring. Now, we have been in this business for about 20 years, as you have seen at the very beginning. And one of the main ideas in this business is that packets never lie. So it means that if you are able to monitor traffic, if you are able to look at packets, so if you are able to make some conclusion based on packet evidence, then we are right. Unfortunately, this is not always the case, and this is not that simple. First of all, because the trafficking is increasing continuously, so we have more and more to process in order to answer this question. Also because the traffic is changing. If you have to look at 5-10 years ago, the traffic patterns you were able to see are very different from what you see today. So you see there are big content delivery networks. You will see that the IPv6 is becoming more and more important. We see that security is another interesting problem to face with. But there are other changes in protocols. As you can see, encryption is becoming, a big problem now, because we are unable to look at the traffic content, but we have to look at the traffic packet without going too deep into it. So this has put a lot of pressure on people like us, that we had to improve our the packet inspection toolkit and our application to take into account these new changes. So packets are good, but they are a sort of a problem. And if I have to look back at 2009, this is a picture of what we have done about 10 years ago. So as you can see, we were talking about packets. Okay, so we have a network. From the network, we try to extract some packet with a tap or a mirror. So we process this traffic as fast as possible, and then based on the packet we receive, we produce some metadata. Again, this was 10 years ago. If I have to look at 2019, this is an example from our open source ntopng application. You will see that there are some nice graphs at the top, in red, where the data is stored on Influx, and ntopng is saving metrics, storing metrics into the database and retrieving them. But still, we are talking about packets. So it means that the faster is the network, the more packets we have to process. And this is a problem. Not just because of the volume of the traffic, but also because conceptually, there is no evolution in this business, because we are still doing the same thing we have done 10 years ago, simply faster, and we had to face with new challenges such as encryption or new protocols, but nothing really happened into this market to make this market a little bit different, because we are still talking about packets or a compressed view of the packet that is called the flow. So it means that we try to group packets with the same 5 tuple, the same protocol, source IP, destination IP, source port, destination port, into something meaningful that is compressed with respect to the packet, because it contains less information. Now, how can we improve this? How can we go beyond this? Because like Daniela said, in modern environments, there are containers, and containers are very dynamic. Whereas here we see that the dynamicity is on the number of packets, but the number of interfaces is very static. So we have to face with something different, and we also have to face with the fact that packets are not able to tell us everything. So for instance, in order to monitor Skype traffic or any application that is using a protocol that is not documented, we have to do the packet inspection, we have to do other techniques to try to group the traffic according to a certain application. So we have to fight against the complexity of this business. Instead of, for instance, using a different approach, that means let's have a look at what the application is doing on the system, and let's bind traffic to the application so that we are sure 100% that we are doing a good job without having to deal with the complexity and the number of volume of packets that are present in modern network. So in essence, packets are still a good paradigm. In many environments, are the only choice we have. But on the other hand, we have to also look at the systems, look at the way people are deploying services. And this is radically different from 5-10 years ago. And therefore, the answer we have to provide have to be a good answer with respect to this changed environment. We cannot say, give me a mirror port where I can see all the traffic of all containers, and then I will try to glue everything together, because this is not a good answer, because we need some extra tools that are able to give us system introspection, so that it's possible to classify a certain traffic with a certain container or service. In particular, containers have changed significantly this market, because in a way, if you look at this picture, they are a lightweighted version of machine virtualization. In essence, there is no hypervisor. And what you can see is that all the containers are sitting on top of the same kernel. So it means that they're very lightweighted, they're portable, they provide a way to isolate processes one from another. And also because of that, because they're very cheap in terms of resources, people tend to use them very often instead of running them as a processes. And the market of containers started basically in 2013. I mean, the new market, because containers have been out, at least this type of technology used by containers by since much longer. They started in 2013 with Docker, basically. And today everybody is using that, not just because they are very good, but also because they allow to change the way applications are designed. In fact, if you look at modern architecture, so we move from a monolithic architecture to a microservice-based architecture, where everything used to be generated or produced by a certain machine, a certain server. Now we are talking about microservice. So we have a certain service that provides something very simple, and that everything is orchestrated together. And then we have the ability of providing or enabling scalability that was a little bit more complicated with a monolithic architecture. In fact, if you look at the fact, we see that usually each microservice is stored inside an isolated container that has its own memory, its own functions. And the nice thing about containers is that the container can be written, can contain software written in any language. So in the past, it was necessary, let's say, if we are talking about Java, to write everything in Java, because all the components have to be compatible, they have to speak each other. But now with containers, this is no longer required. So it means that each container can contain a service that is created by a different programmer with a different mindset, as long as the service is providing what we expect is good. And this allows to scale up, because we are able to improve the performance by simply spawning new containers, and there is an orchestrator or a balancer that is balancing the traffic across all of them. In case something goes wrong or the microservice crashes, the rest of the system keeps going. So there are very big advantages. So because of that, monitoring had to face with this change to make sure that it was possible to look not just at the traffic that is entering and leaving the physical host, but also at what is inside the container, because sometimes if the service is not responding as we expect, might be that there are some interaction between two containers that are not optimal. So we have to look at this type of things. So therefore, when we deal with containers, we have to deal with the fact that, for instance, typical things such as the number of interface or the interface name is very dynamic. So as soon as we start a new container, a new virtual interface is created. This interface is bound to a bridge, and therefore, the complexity and the topology of the system is changing based on the load, based on the type of containers, and based on the system that is hosting the container. So everything is very dynamic. It's not as in standard network where, as soon as you wire a system and you plug a server to a certain port, you are done, and this will not change for a long time. Here, everything happens. For instance, now we are running this webinar, and might be that we need to spawn new containers because we want to handle this workload properly, and at the end of the webinar, everything will be turned down. So it means that we have to face with some dynamicity that, in general, network monitoring is not able to deal with. So this is another interesting thing. So you should not see this as a problem, but you should see this as a challenge. And it's interesting not just to answer positively, but to make sure that we are able to have a solution that is still able to monitor a traditional network where there are no containers, but that also allows to see a visible interaction across containers that are run inside the same system or virtual machine or host. So in essence, we want to improve visibility. This is what network monitoring is about. And it's very important that we are able to speak the same language that DevOps are speaking. So like Daniela said, we have to talk about pod, container, namespaces, Kubernetes, Docker. So we cannot simply say from this IP to this IP, but we have to give a context. And this is very important because the message we have to give is something that should be meaningful for the DevOps that are talking about those terms. So we don't have to forget, however, that a container is running on a physical infrastructure, and this physical infrastructure is running or is monitored through protocols such as SNMP, NetFlow, or IPFix. And those protocols are there to stay. So it means that they are used to monitor the physical infrastructure on top of which the virtual infrastructure is created. So it's important to give a message that says we are still able to monitor the current network, and we're able to monitor modern containerized systems, not just to say from this day we'll move to containers and we are not able to see what is happening on a traditional network. But it is very important to have a system that is integrated. Don't create two different systems that don't speak each other, and also to put this data into a database such as Influx in a way so that you can read the data, you can create different dashboards depending on what you want to show, but in the same way. So don't change your mindset. The data that is inside the database has to be purified, has to be interpreted by intermediate systems that are able to give you visibility on the legacy network and on the new network. This is very important from the same monitoring console. So before moving to eBPF, that is something pretty new for the Linux system, let's talk about something that existed for a long time inside Linux. There is a type of socket called Netlink, okay, that is used in Linux to do IPC in essence. So it's possible to talk from the kernel to user space and to exchange some information. Typically, this is used for monitoring networking configuration. So for instance, the popular IP Route 2 tool is using that to see how the system is configured and to inject or remove rules. If I have to look at Netlink from the monitoring perspective, it's possible to use a Netlink also for monitoring socket. And sockets are the basis of communication inside Unix operating system. Unfortunately, Netlink is not very advanced because the only events that Netlink is giving us are the events for destruction. So it means that whenever a TCP or UDP socket is destroyed, so we receive a message. So we are able to see what happened before, but we are not able to see in real time what is happening, or to see as soon as a connection is created, a message that says there is this new communication. So Netlink is a good idea, as I will show later in this webinar. However, it needs to be complemented with something more dynamic that is triggered as soon as an action is performed. And this was the reason why we jumped onto eBPF. If I have to talk about BPF, that stands for Berkeley Packet Filter, I have to go back to 1997 when Steve McCain and Van Jacobson from Lawrence Berkeley Lab introduced this as a technology for filtering traffic. And this is a very popular technique used with tools such as Wireshark, TCP dump, and so on, that allows to capture traffic and to filter the traffic into the operating system kernel, so that only packets we are interested in, so let's say TCP and port 80, are sent to user space, and all the rest of the traffic is not delivered, so that we can improve in terms of performance and overall data exchange. However, the way BPF was implemented was limited only to packet filtering, and this was the reason why it has been renamed to CBPF, so classic BPF. This means that the lessons learned from the original BPF have been applied to the new eBPF, that E stands for extended BPF. That is in essence a virtual machine that is run inside the Linux kernel, that allows you to run and inject some code from user space to the kernel, and the code runs inside the kernel. This is very important because it allows us to move our monitoring metrics into the kernel and read them from user space without doing the typical path that allows us to send everything from the kernel to user space, because this is much more costly. Because one of the things that I want to stress is the fact that monitoring has to be cheap in resources. Monitoring doesn't have to influence the system, so the CPU load, memory usage, and so on must be very, very limited, if any. That means that monitoring is not changing the way the system is working, but is simply providing you visibility without putting too much pressure on the system, because otherwise people wouldn't run monitoring tools. The way eBPF works is the following. We create an application, usually in C or Python, and this application is divided in two parts. There is some code that is injected to the kernel that is basically run inside the kernel, inside this virtual machine. Is native code, so it's very efficient, and that is used to collect the metrics. And the metrics are sent to user space through a pipe. So therefore, user space applications are not doing much. They are simply waiting for new events that are produced inside the Linux kernel. And when we talk about containers, we have in essence to do this. Whenever we receive an event, so let's say a TCP connection, in addition to the typical IP source, IP destination, and ports, we have some extra information that can be collected from the task associated with the event. So in essence, we can retrieve container information, process ID, group, user, and so on. So in essence, what we have to do is to inject some code into the Linux kernel that can register some hooks to typical function where, let's say, a connection is created, a connection is destroyed, or whenever there is a retransmission, and then to make sure that the kernel is delivering to user space specific events when something like that happens, and do not send to user space events for every single packet that is processed by the system, because this will jeopardize the whole performance and will put a lot of load on the system, and that will make monitoring a nightmare. This is not what we want to do. So therefore, for us, a container is simply extra metadata attached to a packet, and this metadata can be read only if we put the probe inside the same system when the microservice and the container is running. So what I will be telling you later in this presentation is that a typical topology or typical deployment is to create a privileged container inside the system where we are running our services, that it is able to read this information, but that is itself a container. So that means that you will have the ability of running this extra monitoring facility in a very simple way. It can be managed through the same infrastructure that you are using for running your services. So this eBPF is very interesting because it's very cheap, talking about the performance and the computation. It can track system calls, so every communications in essence. And because eBPF is part of every modern Linux kernel, we don't have to add anything to Linux, because this was a problem when we started in 2014 to do some early experiments on this. At the time, we played with sysdig. One of the things that people don't like is to modify the kernel, to add additional kernel modules. And eBPF is great because being part of every modern Linux kernel, we simply have to run our application without having to load any new kernel modules that might invalidate maintenance of your system. In order to avoid people dealing with low-level details and kernel data structure that are not very simple to handle for everyone, so we have created an open source library that we have called eBPF Flow, that is available on GitHub. At the bottom of the slide, you will see the URL that allows you to interact with the kernel without having to know much about the kernel itself. But it allows this library to register some hooks into the kernel that are able to instrument the kernel to deliver to user space specific events whenever something happens. So whenever a communication is created, a UDP packet is sent to a new destination, or whenever there is a retransmission, that there is something meaningful. Because a typical problem of network monitoring is that whenever we want to monitor, let's say, unlikely events such as retransmission or a window change, we have to monitor every single packet of the communication, try to mimic what the two machines are currently doing. So in essence, they are changing the window size, or they are planning to transmit a packet. And this means that we have to monitor every single packet, whereas in this case, we simply have to put a hook into the kernel that whenever the Linux kernel calls the hook for retransmission, we intercept this call, we say, there is a retransmission for this communication. That is very lightweight. It's a safe assumption, because we know that this is a retransmission, not just because we had to reconstruct or to imagine that was probably a retransmission looking at the packets, but we have this as an evidence that is coming from the Linux kernel. So it's also something we can trust compared to packets that might be there have been a packet loss that is invalidating our findings. But this cannot happen with eBPF simply because we are reading that from the kernel. We have a C++ and Go support done my colleague Samuele, and this library, like I've said, is freely available. And on top of this library, we have created the monitoring infrastructure that I'm going to talk in a moment. So in essence, years ago, we have created a tool called nProbe that is a network sensor that it is able to turn packets into flows that are exported according to the NetFlow or IPFix standard. So therefore, that every collector can understand. And based on this probe, we have created an extended version of the probe that is able to interact with the system and to report information about containers. What I want to tell you is that in this tool, we have tried to merge two different technologies. One is eBPF, I just introduced, and one is Netlink. Why that? Because eBPF runs on modern Linux, so on modern Ubuntu, kernels, this is not a problem, but already on CentOS 7 that has an old kernel, then we have some limitations in terms of eBPF, and this is not probably something that everybody will be happy to hear. Another problem is that with eBPF we must be super users. So in essence, this is not a big problem because this application is a monitoring application. But in a way, sometimes this is a problem. People don't like this type of things. So instead, with Netlink, we are able to run basically on any Linux kernel version, because this has been part of the Linux kernel for a long time, and we don't have to be root at all. So this means that we are able to monitor not just this environment that I'm talking about today, but also systems where we don't have root capabilities, and this is a very important news. Unfortunately, the difference between eBPF and Netlink is that eBPF makes sense whenever we want to export information about flow creation, termination, or update, like I've said, whenever there is a retransmission. But it doesn't make any sense to put inside the Linux kernel a hook that it is called whenever a packet for a given flow is received, because otherwise we'll be putting too much load on the kernel. Because of that, our probe is using both eBPF and Netlink, because Netlink allows us from user space to periodically poll the status of the communication present to the Linux kernel and to read this information. So eBPF is promptly reporting a new communication or failed communication. So for instance, you're talking with a TCP port that is closed, and Netlink instead is reporting us information about the number of bytes, the latency, the round trip time, this type of information that is currently present into the Linux kernel. So this allows us to have a probe that is very cheap in terms of resource usage. In fact, just to give you an idea, this probe that we have created called nProbe Mini, as you can see, is using less than 1% of the CPU and very little memory, because we don't have to store any flow information in memory as a typical probe will do. But we simply have to read this information and transmit this to a remote end that can accept this information and treat this as a standard flow, as with IPFix and NetFlow. And this is a very good news, because it means that we are able to monitor a system without putting almost any zero load on it, because we don't have to use as much memory as the number of containers that we are monitoring, and the communication between the probe and the kernel is limited to new communication or to periodic updates. So we are not really paying a fee for every packet that is exchanged, but we are very efficient in terms of resource usage. Just to give you an idea, this tool is talking with remote services through JSON, and it's able to see, as you can see in this example, this is a typical example of communication. First of all, we see an accept, so a communication is accept. In this case, we are saving data periodically into InfluxDB. So there's an accept and then a close. So it means that we are able to monitor, the beginning and the end of the communication, and to receive, when we close the socket, also an update through Netlink of the number of bytes that's been received, or periodically, let's say every minute, we see an update and about this data. And because of that, we are also able through Netlink to monitor a socket that in listening mode. So it means that putting this container inside our system, or using the tool standalone on a non-containerized environment, is possible not just to see the traffic that is exchanged, but also the sockets that are open, similar to what you do with Netstat. So it also allows us to inspect a remote system to see what type of services are deployed, and there is a new port that is used by a given process, because if you look at this log, you will see not just the port, but you also see the process, the user ID, and I will show you later even memory and CPU usage. It's important to characterize the traffic not just based on IP and port, but also by process and by user, and to see if somebody has started a service that was not supposed to start. So this is a very important information. In addition to that, through Netlink, we can provide information that is similar to what sFlow or SNMP counter information is making. With the exception is that in our case, we not only provide you, let's say, interface error or octet in, octet out, but we also provide a context. We can tell you exactly what is the container that is using a certain visual interface, and what is the traffic created by a certain container in and out, so that we can characterize the communication between two containers, so across containers running on the same system, and also to see what portion of the traffic sent over the internet belongs to a certain application. More in detail, as you can see, the information is divided in a few parts. So on the green part, you will see information about the processes, so about who's doing what. So what is the process that's creating a certain communication. In the blue part, you will see standard data that you expect to see with NetFlow or IPFix, so basically the 5-tuple. And in the red part, you will see information about the container. So what container is generating what information. So it means that it's possible to correlate this information. And if there are two communications inside the same host, it's possible to see two flows, one towards client towards the server and the other the opposite, so that we can see both the container peers and to characterize fully the container, the process, and the user. Talking about the Netlink, we will see that in the middle there is an orange part that we don't see with eBPF, because eBPF is just at the beginning of the end. Like I've said, we don't read traffic stats from eBPF. We just have that for events. And inside Netlink, it's possible to read things like the number of retransmissions, the latency, the number of bytes, the current rate, so that we can also see and perceive how the system sees a certain communication from the TCP standpoint. And contrary to many other systems that are limiting their visibility to TCP, we are also able to see also UDP communication. So now, just to wrap up and to see how this system is used in practice, just imagine that our tool ntopng is receiving flows from nProbe, so the nProbe mini instances, and we inject this data into Influx. So in essence, you will see Influx as a database that will contain additional metrics in addition to those that you already have, that contain some tags. So we can say exactly this traffic is generated by this host, by this application, or by this container. And everything will go inside Influx the same way you're using today. We have several ways to deploy the tool. So in one case, we can deploy the tool on a packet-only deployment. So in essence, we don't have an nProbe mini running on the host, the physical host. So we have no container visibility. So in this case, through nProbe, we collect packets, we generate flows that are sent and stored into InfluxData in metrics according to host protocols or application protocols. This is the standard way of running, let's say, the system in a packet-only environment. And now we add extra metadata with the work we have done. So if we install into all hosts, or at least some of the hosts, nProbe mini, it's possible to export not just packets, okay, but also to export extra metadata that allows us to characterize who is doing what containers, what process, what user, how much memory, things like that, and to store this into Influx. So with Influx, you can create a dashboard, let's say, of traffic generated by a given container or by a given application. This is another way of deploying it. And the third way of deploying it is in a fully packetless environment. So in essence, you install nProbe mini in a privileged container into your system that is then able to monitor all the containers running on the same host. And this nProbe mini will deliver through JSON flows to ntopng that we store them into Influx as metrics, so that you can see exactly the same information that I showed you before with packets, but in a very lightweight version, because we are able to characterize the traffic based on the application that is generating the traffic, so that whenever we see, let's say, traffic generated by the Skype.exe application, we can say this is Skype for sure, not just because we do DPI, but because we are sure that this is the traffic generated by this tool. And that is possible to do that in a very lightweight fashion, because like I've shown you before, we don't use memory based on the number of containers, on the number of communication. We don't use CPU based on the number of packets that are processed. But due to this approach, everything will be lightweighted regardless of this number. Just to show you some reports, you will see here that in ntopng, this process view, it allows you to say, okay, this communication between one host and the mail server is IMAP-S, so secure IMAP. And you will see that on this host, there is an application called Thunderbird that is running from a GNOME shell, and that the user, it's me, it's Luca. As you can see at the bottom of the screen, the memory used and the peak memory. All this information is read by nProbe mini on the remote system, is delivered through JSON to a remote ntopng. This is another example of pod container view. You will see that the list of containers, so if you're talking about Docker, or the list of pods if you're talking about Kubernetes, and everything is put into the context, so you can click on every container to see, for instance, what is happening. So in this example, I clicked on the Ubuntu test container. You will see that inside the Ubuntu test there are certain communication. So there is an host that is talking with another process running on the same host, you will see exactly the username that usually in containers is root. You see that there is a telnet to the SSH running on the same system. And this allows you to see through those contextual menu and to filter the traffic based on container, layer 7, flow exporter, because ntopng can collect the traffic coming from multiple containers. And this is very important in case you have a cluster of machines. And like I've said, all the metrics are stored on Influx, so you can use ntopng to read this information and to interpret this information, as you can see in this graph, or you can create your own dashboard on Influx using your favorite tool, because all the monitoring metrics will be stored there. You can also trigger alerts based on the information that you store there. Let's say if you're saving the traffic or the memory used by a given application, in case there is too much memory or the latency of the communication exceeds a certain threshold, you can emit an alarm automatically using the Influx facilities. This is another view. It's what I told you before when I talked about SNMP sFlow-like view. So in essence, through Netlink, it is possible to export information about the interfaces. So you will see that we are able to contextualize a visual interface with a container name, and it's possible, if you click on the graph, to go and retrieve from Influx the amount of traffic generated by a given container at a given time, and to see also how the interaction between containers are using your available network capacity. And it's possible also to put a stacked graph of all the containers, all the container traffic. So in essence, you will see here through this system the same information you're able to see on an existing ntopng system monitoring traditional packet-based network, but simply adding extra metadata that allows you to contextualize better the traffic with the container username or pod. So just to wrap up, in essence, we have now presented a way to read information from a containerized system and inject them into Influx, so that you can create your own dashboard based, let's say, on Chronograph or Grafana if you want, or use ntopng itself to read this information from the database and to display your report. In a way, our system is transparent to the user, because like I've said, we can deploy an extra container on the physical host that is reporting this information and saving this information into another container that is running InfluxDB. The system is very lightweighted, so this is very important, and it uses both eBPF for reporting prompt information about new communications that have been created, or things like a retransmission that are very relevant for network monitoring. And through Netlink, we are able to periodically monitor and update metrics about communication, so that it's possible to report not just typical byte and packet counters that you will read from NetFlow or IPFix, but also more important metrics such as latency, retransmission, or the capacity, the link capacity of the communication between various hosts, processes, and users. So it allows you to give extra information to an existing monitoring system. I don't know if you have some questions for me.
So thank you, Luca, for this wonderful presentation. It shows the value of reaching out to additional resources and sources of information, so you can have a complete view. I have some final remarks as well that I'd like to share with you. Let me go to presentation mode. Sorry. So just to wrap up, from a joint partnership between InfluxData and ntop, what we want to emphasize are three main values and points that you should keep in mind when looking for solutions to help you, to guide you in your monitoring. Yes, you need the right tool for the right job to do the job right. I would complement. First, we emphasize the value of open source because it's the easiest way to start and expand. You don't know what is the next metric or next metadata that you need. As Luca has shown you, there is a history of discovery of new ways of getting more and more insight into what is going on from the inside and from the outside. So you need to be open to exploring, the data in your system, but also attaching to other solutions to complement that view for a more insightful information. You need to be purpose-built because we are talking about a huge amount of data that you are collecting, correlating, processing, and graphing to you. So in order to be performant, you need to make decisions in your design with that goal. And effectiveness is the key word in this market. We are running against speeds that are faster and faster in any aspect of your network. Is the network traffic, is the processing of your application inside of the system. So there is no room for guessing. You need to focus. You need to be able to bring all the information that is available to you to one place, and that includes metrics that matters and metadata that matters. And you need to be able to correlate everything so you can generate graphs or reports that are meaningful to the audience that need to act in real time. So that's basically wraps up what we had for today's webinar. I just would like to point out some of the upcoming events. ntop is hosting a conference in Padova next week from 8 to 9 of May. We also are hosting a conference, Influx Days in London from 13th to 14th of June. Luca Daddy will be there, presenting and answering questions and sharing his insights and experience in the network monitoring market. In our website, also you will find more resources like web tech papers and webinars. Now I would like to stop and open the webinar for questions.
All right, great. Thank you very much. We have just a couple minutes left to the top of the hour, so I think we'll be able to get to maybe one question here, and I will throw it out at you now. How do you deal with nProbe_mini if no privileged mode is available in the container?
Yeah, so in this case, it is not possible to run the eBPF part of nProbe mini. So we'll be running only the Netlink part. So it means that you will not be able to see immediately when a flow is created, but you will see periodic updates and a notification when the flow is deleted. So this is the only limitation, but you're still able to do monitoring, of course, in a bit more limited.
Okay, all right. Next question, can you identify the name of the application running inside of the container?
Yeah, absolutely. We can identify the application name, the user, the father of the application, the memory usage, CPU, typical metrics. It all comes for free with the flow information.
Excellent. Okay. All right, great. Let's see. I think we can get to one more quick question here. Can you talk about how you are able to obtain the networking information since it is not available on the wire?
So in essence, we are running the nProbe inside the system. So nProbe mini is, like I've shown in the presentation, can be running in two different ways. So one in a pure packetless environment, so we don't see anything about packets at all, so we simply see metrics, or combining existing metrics that you can receive through packets. So let's say you have a host, and this host is serving, let's say, remote users, so you will see HTTPS traffic, but you want to say, okay, now that I see this traffic, I want to know what is the application that is delivering to a remote user this traffic, so namely the container ID and the application process. So in essence, this is done by monitoring the interaction through eBPF between the application that is delivering the data and correlating it with the network traffic using the 5 tuples. So in essence, the IP information, IP port are used to correlate metadata generated by eBPF with traffic information. So this is the trick that we use.
All right, great. Okay, well, it looks like we are just about out of time, so I'm going to go ahead and close out the Q&A for this session. If we didn't get to your question, please know that the folks at InfluxData will be getting a copy of all of the questions, and I'm sure they'll be more than happy to follow up with you offline. Before we close things out, I know I promised a drawing for 3 $50 Amazon gift cards, so we'll go ahead and do that real quick. Our first gift card winner is Sylvina Bosch. Congratulations, Sylvina. Our second winner is Marvin Wheeler. Congratulations, Marvin. And our third winner today is Tom Witten. Congratulations, Tom. Also, before we close things out, want to remind the audience that today's event has been recorded. So if you missed any or all of it, or if you just want to listen to it again, you'll be able to do that. It is going to be, you'll be receiving an email actually that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website. So you can always check for it there. Just go to the webinar section and click on demand, and it should be there waiting for you. While you're there, please check out the other webinars that we have both upcoming and on demand. Hopefully there'll be one or two that pique your interest. Right now, top of the hour, looks like we're going to be closing things out now. But Daniela, Luca, thank you both for giving such a great presentation. Appreciate your time. And want to thank the audience today for joining me. This is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody.
Thank you.
Bye-bye. Thank you.